So welcome everyone. So in continuation with our last class, we have been learning and talking about the Sommerfeld model. All right. So what Sommerfeld proposed is that the electrons inside the solid are free electrons and they are non-interacting. All right, they do not interact with each other and also with the positive ion force in the solid which are present, and neither do they interact with the impurities and defects in the solid. In the Sommerfeld model, which was basically a quantum treatment, you consider, so let me just write, yeah, Sommerfeld theory, continue. All right. So what we considered is a cube, is a cubic box with dimension of L. Each side has a length L. The length, breadth, and the height has a length scale L. All right. So you have a cubic box-like structure. Fine. What you had is a cubic box. All right. So each side has length L. This also has length L. This side also has length L. So the electrons are trapped in this box, which is the counterpart of the solid in real life. All right. So the particles are confined by this infinite potential in 3 dimensions, but they are free to move about inside the box. So solving the Schrodinger equation, which is minus h cut squared over 2m e2 grad. Let me write gradient grad squared. Grad squared psi is equal to psi n is equal to en psi n. All right. So depending on the wave vector, the momentum is given by h cut. P is the wave vector and P is the momentum. So if the wave function is psi of xyz is the wave function, So psi x yz can be written as plane wave solution, because you can see that solving this will get the form of the Schrodinger equation which satisfy both sides of the equation. So we take the form of the wave function as plane wave solutions. Let me check if it's recording. Yeah. So we are taking plane wave solutions. So plane wave solutions of free electron, because the electrons are free to move about inside this cubical box. All right. So now normalizing, you will see that this psi naught, if you normalize this wave function, psi will have the form of 1 over root b, v is the volume of the box, times e raised to I k vector dot r vector. R is their position vector. So some of this consideration was that as we recap that for a particle confined in a potential box in 1 dimension, let's say, the wave function has to go to 0 at the boundaries. But Sommerfeld said that they needn't go to 0, but they should obey a periodic boundary condition. So the wave function has to obey Sommerfeld. So this is just a recap from earlier class. Sommerfeld considered that the wave functions in the solid of the free electrons wandering about inside the cubical box here considered in the model. Consider a cubic box. So the electrons are moving about, wandering about freely inside this box. All right. And we are taking plane wave solutions for these electrons to satisfy the Schrodinger equation. All right, so we consider that the wave functions have periodic boundary condition. Periodic boundary condition. All right. So what does this mean? So psi is a subscript of k denoting the wave vector. X is equals to, let me just write down in one dimension, is psi k x plus L. This is your periodic boundary condition. And this was done with the idea that had the wave function gone to zero at the boundaries of the potential box, then it means that the electrons are reflecting from the walls of the container and they satisfy the solution of a standing wave. And standing wave does not denote a propagation of the wave vector. So for propagating solutions, you have to consider the periodic boundary conditions. Reflection from the side walls of the container will mean that they will produce standing waves, and standing waves will do nothing in favor of our theory of what we are trying to get into. All right, so periodic boundary condition. So it was like this. So earlier you had a box, and the wave functions were like this. This is the base offset, and the wave function were like this. It go to zero at the walls of the container. All right, and this was for higher modes. So the wave function goes to zero at the boundaries of the walls of the container. All right. So, but now what you have is you have this box, and instead of going to zero, the wave functions can behave like this. So this was your, so the wave function did not go to zero at the walls of the container. So putting this, psi k x is equals to psi k x plus L. If you put the form of the wave function, which is 1 e raised to I k vector dot r vector is equals to 1 over root v e raised to I k vector dot. So if this is your in one dimension, we are doing all this in one dimension. So let me just write x. All right, x plus L. Fine. So cancelling out both the terms, 1 over root v e raised to I k dot x, we are left with, this implies that we are left with e raised to I k vector dot L vector is L1, sorry, is unity. So this will automatically impose some restrictions on choosing of your x. So this is kx, x. So kx is 2 pi over L times n, where n is 0, minus 1, plus minus 2, both positive and negative integers included. All right. So this was the restriction on the wave vectors if you have your periodic boundary condition. So this, all right. So this was the restriction that the wave vector needs to have. All right. So similarly, if you are talking in this is all about in one dimension. In three dimension, the wave vectors can be deconvoluted into psi k x y z product of this can be written as a product of psi k x x times psi k y y times psi k z z. And each of these wave functions, with the imposition that they needn't go to zero at the boundaries, they need to only follow a periodic boundary condition. In that case, it will have psi x y z is equals to psi x plus L, comma y plus L, comma z. We considered that the box was symmetric, so in each dimension, the length is L. All right. So if you see now, kx will be 2 pi nx over L. Similarly, it goes with ky and kz, 2 pi ny over L, and kz is your 2 pi nz over L. Because in the three dimensions is isotropic, so they are not dependent on each other. So for each wave vector in a direction or in a dimension, you have this imposition that kx or ky or kz have to be 2 pi by L times some integer which can be 0, plus minus 1, and plus minus 2, and so on and so forth. So these are your definition of momentum states. Sorry, this mess up sometimes. So these are your definition of momentum states. So these are your definition of momentum states. Fine. All right. This is what you get in three directions. As we are considering working in 3D, there's this imposition of the restriction on this wave vectors. All right. So your nx, ny, nz can be 0, plus minus 1, plus minus 2, so on. Similarly for this also. All right. So this is the basic imposition that you have to do. So now this define this set of integers. This set of integers define discrete momenta states, because all possible values of kx, ky, z are not allowed, because in that case, because if you're using quantum mechanics to automatically have this quantization of the wave vector, because not every value of the wave vector is possible. There's only certain integers that will be multiplied to 2 pi over L, where L is the length of the system, or the or in this case the cubic box that you are considering. So it will be only integer multiples. Discrete momenta states. This is quantization. All right. So now, recalling that our n, which is the total number of particles, the n was given by 2 times k Fermi-Dirac distribution epsilon k minus mu, where mu is the chemical potential. All right. So, and this is for spin degeneracy. And this 2 is for spin degeneracy. All right. So this was your total number of particles. But remember that at, sorry, write a different color. At T equals 0 Kelvin, your mu is EF, which is the Fermi energy. So at 0 Kelvin temperature, Fermi energy defines the energy level up to which the electrons are fulfilled, and beyond that, it is the energy levels are vacant. So this is the maximum energy level up to which the electrons are filled. So this was just a recall. So as I said, the momenta states are discrete. So possible momenta states are like this. Momentum, this misaligned the line. So momenta of electrons in the solid, which is kx. So I interchange between wave vector and momenta, kz, which will be, you can have 0, 0, 0. You can have 2 pi over L, that is in the x direction, n is 1. All right. You can also have 0, 2 pi over L 0. You can also have 0, 0, 2 pi over L in the z direction, and also 2 pi over L. Like I said, it's only integer multiple of 2 pi over L in each of the three directions. So these are the discrete momenta states that the electrons will possess. And this is because of the imposition of the boundary condition, that of the periodic boundary condition. All right. So this is what we get. Fine. So now, as I told that there are discrete momenta states possible. So if I have to draw a graph of this kx, ky, and kz, this is kx, and this is your ky, this is your kx, and this is your kz. So now all possible momenta states are discretized. So like this, you'll have discrete momenta states in each of the positive and negative directions of kx, ky, and kz. Fine. This is how you define the momenta states. And this follows same for all the directions. These are the momenta states. All right. So now, if you draw a unit volume, so what can you have? So in between these discrete energy state, momenta states, you can't have any other momenta state, because only these discrete momenta states are possible. So the smallest volume that you can have is of this one. So you'll have this cube drawn. All right. So if you draw a cube which defines the unit volume, the smallest volume that you can possess. So let me write it. Smallest volume in this momenta space. Smallest volume in this momenta space will be given by what? 2 pi over L for kx, 2 pi over L for ky, and 2 pi by L over for kz, and which gives you 2 pi over L cubed. So the volume of the smallest box that you can draw in this case space is 2 pi over L cubed. All right. And let me just define it like this. What you have is, this is 2 pi over 10. This is 2 pi over 10. This is 2 pi, because we are working in a symmetric box. Now recalling our counting statistics, which I just wrote a bit earlier, n is 2 times summation over the discrete momenta states. Now you know that you have discrete momenta. How we did that distribution? As a function of ek minus q. And this was our counting statistics. So now at t equals 0 Kelvin, this is modified as n equals twice of k fd ek minus ef, where ef is your Fermi energy. Understood? So at t equals 0 Kelvin, the chemical potential mu is transformed into ef, which is the your Fermi energy. And ek will be given by simply solving a Schrodinger equation h cut square over 2, and now you know that you have plane wave solutions. So putting that in the Schrodinger equation, you will get the energy as h cut squared over p 2m k squared, and this k squared will be summation of the k's in all the three directions, k squared plus ky squared plus kz squared. So now this kx, as I told, this ki is 2 pi ni over L, where I is at x comma y comma z. So now as L becomes very large, in the limit of L going to very large. I mean, your macroscopic box, this is not like a microscopic box that you are working in. In real life, this boxes you see, you are working in such type of system. The solid is like that because the box in our model or the Sommerfeld model is the interpretation of the solid that the electrons are residing in. So in the limit of L going to 0, Ki's will be small and he will essentially have a continuous distribution of Ki's. So in this case, as L tending to very large, in that case, your Ki's will not be discrete, but it will reach the continuum limit. So as I said that it will be in the continuum limit. So the summation, this is over all the K values, this can be transformed into an integration, which is the summation of over K means you have to sum over all the discrete K states or the momentum states. But when you do an integration, you integrate over the volume. This is the total volume. Now, to find out the discrete number of states, you have to divide it by the volume of the smallest unit. All right. So summation K gets transformed into the continuum limit as 1 by 2 pi over L cubed integration d cubed K. All right. And this is your volume integration. Sorry. So, this is your volume integration in K space. Integration in K space. Fine. So what we are familiar with is d cubed R is d cubed. Sorry, this is dx times dy times dx dz. Fine. Similarly, this is in real space. All right. Now d cubed K is dkx, dky, and dkz. Fine. So this is your volume integration in K space. So now if you have to find out the counting statistics, you employ the counting statistics to find the number of particles. You had two summation over K Fermi Dirac Ek. Now this is EF because you are working in T equals 0 Kelvin. This gets transformed to your 2 times 1 over 2 pi over L cubed times d cubed K Fermi Dirac epsilon K minus epsilon F. Simple. Now recalling, how does the Fermi Dirac distribution look like? So if I draw it, this is it. The Fermi Dirac distribution is 1 till a certain energy value EF, which is mu at T equals 0 Kelvin. So this is 1 and this is a Fermi Dirac distribution and this is energy. All right. So after the Fermi energy, the Fermi Dirac distribution goes to 0. And let me remind you that this integration, this is d cubed kx minus infinity to plus infinity minus infinity to plus infinity. Sorry, this is not d cubed. I'm writing it wrong every time. So this is dky times minus infinity to plus infinity dkz times your Fermi Dirac distribution. So the momenta states are, when you are doing the integration, not discretized. It's only from minus infinity to plus infinity. All right. But the Fermi-Dirac distribution, this is Fd epsilon k minus epsilon f. This is 1. Sorry, I'm making so many mistakes. So this is 1 for Ek less than Ef. And this is 0 for Ek greater than Ef. So simply speaking, if you consider also the negative values of k, I mean, it's corresponding to, the Fermi energy, there should be a Fermi wave vector, right? So that the wave vector that it possesses is k. So it will be minus Ef minus Ef E Ef. Energy, this can be written as the restriction. In terms of the wave vector kf, this is like this. So your integration will be not from minus infinity to plus infinity, but from minus kf to plus kf. And in each dimension, it is kf, because kf is constant value, energy value. It doesn't depend on which direction you are working in. So this is the restriction. All right. So let me tell you, this kf is your Fermi momentum. Like EF is the Fermi energy. Corresponding to this energy is Fermi momentum or wave vector, which is given by wave vector, which is given by Ek is equals to h cut squared k squared over 2m. That is known to us. This is the energy. So the Fermi energy would be given by h cut squared kf squared over 2m. So the wave vector corresponding to the Fermi energy is given by kf, and we call it the Fermi wave vector or the Fermi momentum. So finally writing it, Fd, the Fermi-Dirac distribution, is 1 in minus kf. So this will be all. This will be less or equal to 100. Yeah. So this is 1 for minus kf, k times k less than k. So what we have is n is 2 into 1 over 2 pi by L whole cube minus kf plus kf d cubed k Fermi Dirac epsilon k minus epsilon f. So the integration is no longer over minus infinity to plus infinity, but it's over minus kf to plus kf. All right. So now this is L cubed. So this goes in the numerator. So L cubed is your volume. L cubed is your volume of the cube that you are working in. So this is 2v over 2 pi whole cubed times minus kf times plus kf d cubed k times fd epsilon k minus epsilon f. Now, as I told that between minus kf to plus kf, this Fermi-Dirac distribution is 1, and beyond that it is your 0. So what you can write is that this is n over v. You take it to this side, and this is the number density is equal to density of electrons in the solid. All right. So this is the density of electrons in the solid. So this is given by 2 over 2 pi whole cubed. So now Fd is 1 in the limit of minus kf to plus kf. So this is mod k less or equals to kf d cubed k. Fine. So if you can correlate, when we consider d cubed r, it was, and integrating it over some radius, it gave the volume of a sphere. So that was in real space. Thinking similarly like that, you can think that d cubed k is the volume of the sphere in k space. So this is the volume of the sphere in k space, which is nothing but 4/3 pi. Kf is the radius of that sphere. This is kf cubed. Fine. Why this is so? Because in a space, in k space, you have this is k, this is k, this is k z, this is k y, and this is kx. It's in these directions also, and these directions also. So what you can consider is a sphere which has a radius of kf. You have a sphere which has a radius of kf. All right, and the momenta states are distributed discretely in between them. You have these momenta states in this sides. You have this momenta states. You have this momenta states. You have this momenta states spread all around here. Also here, spread around randomly. But because of the Fermi distribution going to 1 less than at k time k equals kf, so the energy levels will be filled up to this Fermi sphere. Let me just explain this clearly. So what you have is your n is 2 over 2 pi whole cubed times 4/3 pi kf cubed. So imposition of the Fermi distribution and the discreteness also, the allowable energy levels are contained within this. The allowable energy levels are contained within this, your Fermi sphere. This is your Fermi sphere. In real space, we used to calculate the volume of a normal sphere. So similarly, in this case also, we are calculating the volume of a sphere in k space. So this is sphere of radius kf. The radius is kf. Fine. So, and this is at T equals 0 Kelvin. So all the electrons that fill up the energy levels, it is only up to the Fermi energy, and the corresponding wave vector is kf. So in k space, in 3D k space, kx containing kx, ky, and kz, the electronic states will be contained within this Fermi sphere. All right. So this 4/3 pi kf cube is your volume of the Fermi sphere. All right, volume of the Fermi sphere. It can also be named as Fermi sphere or Fermi sea. So allowed states are only in this regime. Beyond this, it's not allowed. Not allowed states. States are present beyond kf, but the allowable energy states are only within kf. So this is your allowed momenta states, or you can say energy states. So within the Fermi sphere, those are the only allowable momenta states or energy states. From that, you can have the estimate of the Fermi wave vector. So kf is then given by 3n times 8 times 8 pi cubed times, this is kf cube, this is n, which is 3 pi squared n, which implies kf is equals to 3 pi squared n to the power 1 over 3. So your Fermi wave vector is 3 pi squared n times 1 over 3. So how do we get the Fermi wave vector? We have EF is equals to, sorry, EF is equals to h cut squared kf squared over 2m. This is just a solution of the Schrodinger equation, and at the Fermi energy, this is the form. So your EF, the Fermi energy, will be given by h cut squared over 2m 3 pi squared n raised to 2 over 3. Similarly, you can also have the Fermi momentum, which is h cut kf, which is h cut times 3 pi squared n to the power 1 over 3. From that also, we can calculate the Fermi velocity, which is h cross over m 3 pi squared n times 1 over 3. So Vf is your Fermi velocity. Is your Fermi velocity. Pf is Fermi momentum. So automatically you get all these values from the consideration that you have periodic boundary conditions, and there will be, your momenta states are discretized as a result of it. And with the imposition that you are working in T equals 0 Kelvin, so the Fermi return distribution will have unity value only up to the Fermi energy. So these all give you the values of Fermi wave vector, your Fermi energy, your Fermi momentum, and the Fermi velocity. So now is the time to ask, what is the order of magnitude for the, or the value for this Fermi velocity and the Fermi momentum or the Fermi energy? So how large? Large is the Fermi energy or Fermi velocity? Calculate it in a very common example. Let's say for copper. Say for copper, this is, N, which you calculated in earlier lectures, n raised to 23 times Z times delta by atomic mass, atomic unit. All right, so that gave you 8.49 times 10 raised to 22 electrons per cc. With that, we can put the value of n in EF as EF is h cross squared over 2m 3 pi squared small n raised to 1 by 3. If you put n there, you get the energy of the, you get the Fermi energy. So writing down some values, some common values for some common metals, let's say for copper, let's say for silver, let's say for gold and aluminum. The Fermi energy, which is in orders of electron volt, is 7. This is for silver, it is 5.48. For gold, it is 5.51, and for aluminum, it is 11.63. So you can imagine it is 1 to 10 tens of electron volt. This is very, very large. This is very, very large. In comparison to what? In comparison to the thermal energy. So you can have a corresponding Fermi temperature. How can you have that? You consider the Fermi energy as some Kb times some temperature scale, which is given by Tf, where Tf is Fermi temperature. So to see how high this energy is, in spite of seeing it in electron volts, you can see it in the temperature scale in comparison to room temperature. So the Tf is Fermi temperature. Fair enough. So Ef is kBTF. So then, which implies Tf is Ef times over kB. And using this 7 electron volt over 1.38 into 10 raised to minus 23, which is in SI units, In proper units, it is 10 raised to minus 19 joules divided by 1.38 into 10 raised to minus 23 joules per Kelvin. So this comes out to be 80,000 Kelvin. So you can imagine how large this Fermi energy is, and its corresponding Fermi temperature is that much large. And similarly, if you can calculate this, you can calculate Fermi velocity also, which comes out to be of the order of 10 raised to 6 meters per second, which is some fraction of the speed of light. This is 1% of the speed of light. All right. So now, although you are at room temperature, let's say if you work at room temperature, then also the Fermi energy will be in orders of electron volts. So you can imagine how high this Fermi energy is. So we have to stop in now, because we have done, in this lecture, we have done the calculation of the Fermi energy. We learned about the Fermi sphere and how up to this sphere at T equals 0 Kelvin, only the electronic levels are filled. And beyond that, the electronic states are vacant. We derived an estimate of the number density of the electrons. From that, we got the Fermi energy, the Fermi temperature, the Fermi wave vector, the Fermi momentum, the Fermi velocity, and lastly, we got an estimate of the Fermi temperature and the Fermi energy. So this is your application of the Sommerfeld model. You are doing a quantum mechanical consideration. So let us just stop here, and in our coming lectures we will finish this Sommerfeld theory. All right, we will calculate the density of states and many more things, and we will wrap up this Sommerfeld theory. So thank you everyone. Let's stop here.